Now we will start chapter 4, which is kinematics of a rigid body. We studied kinematics of particles. This time it is for rigid body. Now what is kinematics? Again, kinematics is the study of motion without the force. So here we will not deal with the force, only the nature of motion. Okay, so for rigid body, first translation. Translation means linear movement something. If a rigid body moves in a line, so nothing changes. It's a whole body. For translation, like no changes occur. Like whenever a body is here versus in new axis, nothing changes. The velocity, the acceleration, everything remains same. So here there is nothing to study about translation. The main important thing for rigid body is rotation. When the rigid body rotates, there is some changes or there is something to study. So let us start. A rigid body was like at OA position. After sometimes it went to OB position. That means a body is rotating, similar to a linear displacement. A body from A is moving to B. That means A to B is the linear movement, but the angular movement delta theta, it is that angular displacement or angular movement. So yes, if I see the equation, so angular velocity is same thing about linear, is displacement by time, but this time it is angular. So delta theta, that means angular displacement over delta t, the time. So omega means the angular velocity. Again, linear velocity, angular velocity, similar concept. It is distance over time. For linear, we take linear distance by time. Here angular distance. Angular distance means the radians that it is rotating, the rotation in radian. So theta by t. Okay, now if it is very small, we can write ds is r d theta. How do we know? From our earlier classes we see that if there is a circle and if it is say r, if angle is theta, this portion is called as equals, now here my writing is not good, r times theta. Now if my angle is theta here, you cannot see, yes, you cannot see, yeah, now you can see, yes. If my rotation is very small, and we can write this one is equal r theta. We saw that many times in our life. Okay, same thing here. This is why ds is r d theta. Now if we differentiate v is ds by dt. Ds means the linear displacement, so this time it is v. So then ds r d theta, then if you do the differentiation, finally we come linear velocity equals angular velocity times radius. Now here is the calculus we use to derive it. So what is angular velocity? The angular displacement by over time. What is linear velocity? Linear displacement over time. What is the connection? Connection is linear velocity equals angular velocity times the radius of the displacement or radius of the rotation. So we should memorize or note this equation. We need this equation. Similarly for acceleration, again linear acceleration, a is linear acceleration, alpha is angular acceleration times radius. So linear acceleration equals angular acceleration times the radius. Now this acceleration is tangential acceleration. Whenever a body moves around a circular around an axis or in a circular path, there will be two acceleration, normal and tangential. We'll talk about normal. Yes, maybe here, yes. So normal acceleration is v square over radius. We saw that equation in our linear kinematics also. And normal acceleration is v square over that time it was rho means radius. So now the path is circular, so r. So an is v square by r, v is omega r over square, so finally it comes omega square r. So normal acceleration is omega square r, linear acceleration is alpha r. So we should remember this. So for angular rotation, there are two kinds of acceleration: normal, one is tangential, and then the combined acceleration we can find using this Pythagoras rule, which is square root of then square of both component. So that is the story about acceleration. We saw the story about um, linear story about velocity times angular velocity. Now this equation, there's a other is one kind like another type of expression connecting acceleration velocity this. So for linear we saw this equation in kinematics of a rigid kinematics of particles. If I open that handout, it is from other chapter, so it's table 2.1 chapter 2. In that chapter we saw for linear motion, a ds equals v dv. A means acceleration, ds means displacement, v means velocity, dv means differential velocity. So we saw that equation. Similar for angular, we write alpha dq. Alpha means the angular acceleration, dq means angular displacement, equals angular angular velocity times angular velocity times differential angular velocity. Similar to this equation, this is for linear, this is for angular. So this equation is to note. The reason is sometimes we need to do differentiation. In that case, we may need to use this equation, at least mark it down. This equation also available in the FE reference handbook. You may need it during your FE exam. Similarly, this equation for linear. Okay, now for constant acceleration we can derive some basic equation similar to our linear. Now I wrote here some equation from our linear kinematics. What is that? B equals b naught plus at. Same thing for here. It is omega, no, omega time t. That means b similar to b. B is linear. This is angular. Now alpha naught t is at. Constant acceleration times time plus v naught. So here omega naught. So same form. One is linear, one is angular. Similarly, this equation, similar to this equation we saw in our linear motion, s equals half at square plus v naught t. Same thing here. Theta means angular displacement, half a t square plus omega t. Now this portion, this theta naught, t naught, t naught, it is just the initial. T naught means initial time. Theta naught means initial displacement, and typically these values are 0. I can write here this value also, b naught t minus t naught, or here t minus t naught square. So t naught, theta naught, it is just the initial, my reference point. Typically those values are taken as 0. Now same pattern of equation whatever we learned from linear equation. Another equation, this equation we saw in our linear kinematics, v square equals v naught square plus twice. Same thing, omega naught square is omega square equals omega naught square twice a s. Now s, I can write here s minus s naught, because this theta naught means initial value. Initial value typically 0 because we start from 0, or whenever we start we take that point as a 0. So this value is most of the cases 0. So again same pattern of equation, just different symbols and different meaning. Why different meaning? One is linear, one is angular. So hopefully I covered whatever theory. Now regarding that calculus, whatever we need similar, say if I open okay, so I opened a new sheet. Say for example in linear and okay, excuse me. For linear motion, we write a equals dv by dt. Yeah. Same thing. Then same thing for angular. We can write alpha equals d omega divided by dt. Same pattern. For linear, we write v equals, say, ds by dt. For angular, we write omega is d theta by d t. So similar pattern. You can see that from here to here, whatever we learned, that is for acceleration, this is for linear, this is for angular, this is for velocity about linear, this is the velocity in angular direction. So if you need to use calculus, same calculus. And we also learned that v equals omega r, linear velocity equals angular velocity times radius. We also learned that linear acceleration is angular acceleration times my r. Now this acceleration, it is a tangential acceleration, because we know that whenever a body moves around a axis or in a circular path, there is a normal acceleration too. That can be found using an. An is v square divided by r. Same thing, we can write omega square times r. We saw this equation. So that is normal, that is tangential, and to find the combined a is square root of this square plus this square. So hopefully I covered the theory, and next we will see some example, so that it is easy for you to understand. I will wrap up now. Thank you.